This is the main screen on which the user is greeted. First, the user has to sign in. When the user signed in, the options are shown to him. These are the options available. The bottle one is now expired. There are two options available. When you select one of them, user is able to bid on this. Currently, this is 1,500. If we select 1,000, then that is lower. Therefore, the app is not giving the opportunity to bid with lower prices. If we try 2,000, now the user is able to place the bid. Then the user who had created this listing gets an email showing that a bid is placed. In here, this is the email. Someone has just placed the bid of 2,000. Next, he is able to create items as well. In creating the items, the user can enter the title, and a description, an image, set the price, and set an end date and time. Then this listing is available. The seller cannot bid to his own bidding. If we see when we place the bid, it says sellers cannot place bids on their own listings. So that's all in the Auction Hub application. The dashboard shows all the listings he has been a part of.
Let me introduce you to our system. Our platform is built on microservices architecture following database per service pattern, ensuring complete service isolation and independent scalability. We have 9 core services orchestrated through event-driven communication, providing a robust foundation for auction operation. When we talk about application flow, let me walk through how a typical auction transaction flows through our system. In the user journey, user enters to the API gateway, which serves a single endpoint for client requests. The auth service handles the user registration and login, issuing JWT tokens for secure communication. Once authenticated, user can generate auctions listing using uh, listings service. Other users can place bids via bid service, and uh, when an auction sends expiration service triggers completion process. Finally, uh, payment payment service processes the transaction through Stripe integration. When we talk about event-driven architecture, our system is relies on ads streaming as central event bus. Here's how it works. When listing is created, the listing service publishes a listing created event. The expiration service consumes this event and schedules auction end time. When bids are placed, bids created events update the listing with the current highest bid. Upon auction completion, auction ended events trigger payment processing and notification. When we talk about uh, our services, internal services, there are 9 services. Email service, we have used as a notification, and auth service for authentication, and we have implemented Saga orchestration. We store this, in Redis the Saga state and monitoring using our dashboard, and the bid service, payment service, expiration service, profile service, and listing service. So when we talk about the security implementation, we have implemented JWT authentication, as well as in the AWS we have implemented roles, uh, IAM roles to each resources, uh, and also in API gateway we have implemented host configuration for and request validation.
In our application, let's begin with Saga pattern. This is how we ensure our data consistency in our systems. In our architecture, we implement orchestration-based Saga with the dedicated Saga orchestrator service. This will service act as a central brain, coordinating with multiple business process like user registration, bid placement, orchestration completions, and payment processing. The every steps we need, we implement that Saga all flows. And in example, in place of Saga, there are multiple steps with validations up to the notification send. The all the status is tracked in the Saga, and if there is anything happen in this flow, therefore all the things that happen is undo, and it's get to the revert back for the uh, consistency for the our data. And we implement the Saga dashboards. Here you can see three users currently created our applications. Therefore we can track in our Saga. It's only now the users are in the profile created. After successfully it's gone in these dashboards. This is the real now productions dashboards we are working in. There is no any Saga means now there is no any active sagas in there. We in here we everything we track Saga ID, Saga types, and Saga states and priority, and everything we are tracking the dashboard. If any Saga activities come to there, if it's complete and successfully finished, then it's disappear in their dashboards. Um, and you can see it in here, but we can track all the things. In here you can see some payments. In example, in the payment process states, you can see there's some multiple states we are used for that one, like as we implemented in there. In our Auction Hub's websites, we implement circuit breaker design patterns. It is act as a proxy for the external services. It's monitor the failures, and if the number of failures exceed of certain thresholds, it strip the circuits. This stop all the subsequent requests for the event trying to reach the failing services for period of times. This prevent a falling services from the overwhelmed by flood of requests. Also, it's time to recover, and it also prevent the failures from cascading to other part of our systems. So we have implemented our circuit breaker packet pattern to place in our system. What is in net service, and other is for the API gateway service. Therefore, we cover the all the system, all the services by using this circuit breaker patterns. In our API gateway for incoming the HTTP request, and in the all the nets wrapper used for each services for internal communication. And so in we are going the Argo CD dashboard. In you can see there is number of services we are deployed, and currently there is a one. There's a we let's check some API gateway healthy pods. In there, when we can look in the logs, you can clearly see circuit breaker is closed. Closed means it's now it's working in normal way. You can see it in here. Then you can see that the circuit breaker pattern we implement this is successfully fetched the request, and it's worked. Therefore circuit breaker is currently closed, and here also closed. We can see in here the circuit breaker configuration. In there, if they have 5 failures, then it's come to the open states. If there is more than 5 states, it's open. If then we have get sometimes wait sometimes, and again it's going to the half open states. In that times it's again try to access that server. If not, again it's open the circuit breaker. If it's successfully fetched, then it's going to the closed states. And in here you can see the 3 states that we implement. And if we fail, it's feedbacks for each services. Now our application's health is degraded. That means some pods are get failure. And you can see there is some number of email service pods and expiration and listing services, and some pods are get failure. When we are looking at some pods, we are need to look the logs. When the logs we are looking, you can see that the circuit breaker is open in now. That means that's endpoints are not working properly. Therefore its circuit breaker states going to the open states. Then you can see the next attempts in that time. In that time, the circuit breaker that halfly open and again send some request. In that times again it fail. In that again the circuit breaker open, it is successful, then circuit breaker is going to closed states. Therefore, you can see the circuit breaker is properly worked. When we look in the server logs, in there you can see if the all the requests are correctly working. In that time the circuit breaker is closed. In that time, if the service is after get some error that the request is not properly worked, in that times there are circuit breaker counts. That configuration we already configuration 5 times, therefore it's counting 5 times that request is failure. Then it's count 1 2 3 and 4 and 5. If all the 5 uh, failure thresholds complete, then circuit breaker open. It's get to the open states. Therefore, you can see in here, therefore circuit breaker is currently now open, and therefore uh, after some times again circuit breaker is come to the half open states. Then again it checks that the requests are working properly or not. It's not, again it's there show the uh, request is falling. Therefore, again circuit breaker count again and again once the circuit breaker is open. That is the circuit breaker happen in the coding. And here is the overall architecture of circuit breaker inside our application. In our applications, we implement bulkhead pattern. It is another crucial resilience mechanism in our architecture. In that bulkhead ensure that is one section spins a leak and floods and damage its container, another ship it doesn't sinks. We apply same principles in our system. In our system, its bulkhead pattern isolate a component resource like thread pools, connections, or memory. So there is a failure or traffic spikes in one service cannot exhaust the resource of another service. This prevents the domino effects of where a falling overwhelms service bring the entire applications. And we implement this at our API gateway where our configuration separate dedicated the resource pool for each downstream services. This overall architecture, you can see how it's integrate bulkhead mechanism in our application, and bulkhead and circuit breaker are working with together for the best resilience. And you can see the here the codes we are implement set the all the services configuration the bulkhead, and we are put the limits of each services how the max concurrent request can put. In our auction system, we implement CQRS patterns, that means command query responsibility segregations. This pattern we are used to optimize the both write and read operation in our systems. We have separate our write model for commands and denormalize to read model for the queries. An example, when a seller create a new listing, and that's command, the request goes to our listing command service, which handle the create writes for the primary database and even publish in our nets. And our listing query service listen for that events, and its role is process that even an update it denormalize read model. This model is highly optimized for fast reading. So search queries in the listing is served by a listing query service. Because its database is strictly specified for reading, we can perform complex search and display thousands of listings with incredible speed by using this CQRS patterns. Therefore, you can see in the listing services, we are creating that CQRS for bit created, bit deleted, bit listing and reading and updated, and everything's we create separately for use of CQRS model. In our auction hub website, this is our distribute tracer. That's mean this is track all the requests and everything's with our all the services. In example, you can see in here, you can see all the services under here. In example, if you are going to like list listing services and find trace, you can under this you can see everything's request and whatever have happened, everything inside we can show it. In example, we click here, you can see how many times it that request will go on, and everything's details we can track it in here. An example that you can that the payment get request gone through the listing service and payment service, therefore it shows in there. If there is a failure or something happen, we can easily track it in here. Therefore we use that for open telemetry and Jaeger UI. In there we are using the trace ID and span ID for the track all the traces.
This is our CICD flow. In here, we are using Argo CD to create our pods in the EKS cluster. I will show the code to create the EKS cluster. Here we are using Terraform. In here, the main .tf file, we have the EKS cluster information and the node group informations. We have the output files, providers, and variables, and also the VPC file. In here also we create the Argo CD during this creation of Terraform. Next we have in our Argo CD, it is looking at this repo, Argo CD Action Hub repo. In here we have all the deployments we need in our pods, the API gateway YAML, auth YAML, bit YAML, email. These are all the microservices in our application. Here we have the infrastructure part, the PVCs, the services, ingress, and also Datadog agent is also included in here. We have secrets in this file. This is not shared into the GitHub. This shows the namespaces included in our EKS cluster. We have also created that as Helm charts too. In Helm charts, we have under templates, config maps, deployments, and infrastructure. Just like the same infrastructure is created here by using Helm charts. We have the ingress, namespace, chart, and finally values.yaml in passing all the values to the Helm chart. This is our Argo CD. In here, all the pods are shown. These are the pods that are running in our EKS cluster. We have auth DB such as auth MySQL, and we have Jaeger for monitoring. These are DBs. The API gateway, auth. These clusters are some are healthy and some are degrading because we are using auto scaling. Auto scaling is here the vertical pod auto scaler and also the horizontal pod auto scaler. Datadog agent is also running in this cluster as shown here. Next, all these data logs are sent to Kubernetes. These Kubernetes logs are sent to Datadog. As shown in here, we can see all the pods statuses. These statuses are created into a dashboard. This is the Kubernetes pods overview dashboard. Here we can see what pods are running and sort them by namespace, the memory usage, and if there are containers that are getting killed, any containers in trash loop backup, container restarts, network errors, all are shown in here. We also earlier used Prometheus and Grafana. Then we moved on to Datadog for monitoring.
So when it comes to Kubernetes architecture, the auction application has several layers. So the main Kubernetes cluster is deployed in the EKS, Amazon EKS. So there are mainly 3 nodes in our EKS cluster. And here is the overview of our EKS cluster. So when users accessing our auction application, they first face the ingress controller through the load balancer. So we use Nginx ingress controller as our entry point. Then after that, there are 2 namespaces. The first namespace is for the application to application and microservices. Then the second namespace, the auction infrastructure namespace for the storage and streaming layer, and also caching layer. So the main namespace is auction system namespace. So in auction system namespace, there are 2 front-end service and API gateway service. So API gateway service is the gateway for the backend microservice layer. Then the front-end service is the what users actually see. So through front-end service, these are the pods. Actually, this is a rough overview. There are secrets and other things. So through front-end pod, they access our API gateway. Through our API gateway, they access our microservices. So when it comes to microservices, there are several microservices are there, and there is the message queue for the net streaming service. and this is the database layer with MySQL databases, and the caching layer with Redis services. So this is the overview of our Kubernetes cluster. So we have configured this with Kubernetes secrets, and also we use config maps for other configurations, and deploy. These are the main deployments we use, and also this is the ingress controller we use. Here we routed the traffic to API gateway and front end using these ingress rules. Also, these are the namespace layers, and these are the services. So this is the architecture of our main Kubernetes layer. So when it comes to auto-scaling, we used horizontal pod auto-scaler and the vertical pod auto-scaler. So this is let's see about the horizontal pod auto-scaler. So this is the horizontal pod auto-scaler architecture. And what horizontal pod auto-scaler does is when the CPU or memory reach our defined level, defined utilizations, it automatically scales up. So this is an example for the front end. So here when resource utilization, CPU utilization is over 70% for some time, it grows. So that means it grows up to 5 replicas, and also it will have 2 replicas running every time. So after some cooldown period, when utilization goes below 70%, it will then automatically scale down. So we can see that in our Datadog dashboard. So here I have filtered out the front end. So in here you can see the CPU usage of the pod. So here CPU usage has peaked. When CPU usage is peaking, you can see the running pods are increasing. The pods running are increasing. So after some time, those pods are automatically got down. So that means this is the horizontal pod auto scaling. Then also we have configured vertical pod auto scaling, but we didn't use vertical auto scaling for update. So we off the update. Then vertical pod auto scaler only provides some recommendations to us. So this is an recommendation provided by the vertical pod auto scaler for the API gateway. So here you can see the provided recommendation, provided recommendation about the lower bound of the CPU target and the ideal usages, and the upper bound where it can go. So here is the recommendation for the API gateway. So likewise, we can see various recommendations for all the configured vertical pod auto scaling units. So that's the auto scaling part. So when it comes to continuous integration part, the developer push the code to GitHub. Then there is our CI agent. The CI agent currently we are using GitHub Runner, and also we have previously used Jenkins. After the CI agent has run, the CI agent will push the build images to Docker Hub, and also update the manifest repo. So there will be a manifest repo where Argo CD will be continuously listening. So Argo CD was used for the continuous deployment part. So Argo CD will continuously listen to this manifest repo. After updating the manifest repo, the continuous deployment part will trigger. So initially we use Jenkins for the continuous integration part, and what this does is after developer push the code, it will provision worker EC2 and then do the build, and after that it will push the build images to the Docker Hub. So we use Docker Hub as our container registry. So later we move to GitHub Actions and GitHub Runner. So here we are using our own GitHub self-hosted runner. Using this workflow, we are building our Docker images and pushing those Docker images to the Docker Hub. In the final stage, we are updating the manifest repo. This is the manifest repo we are using. This is the repo where Argo CD will be continuously listening. So in the final phase of the continuous integration workflow, it will update the Argo CD manifest repo. So Argo CD will know there was an update, and Argo CD will trigger the continuous deployment part.